Okay, so let's start the class. हेलो। हाँ जी, बोलो बोलो। हाँ जी, बोलिए। यार, मैं आप मुझे कल कॉल करो 1 बजे के आसपास, वो टाइम में डिस्कस करते हैं फिर क्या करना है फिर। हाँ जी, हाँ जी, हाँ, we'll have one class in the Google Meet, right? Oh, so tomorrow give me a call around 1. मैं कल डिस्कस करता हूँ, अभी मेरी क्लास चलने वाली है। So let's start the class today. It's our first period. I'm over there. I have to take your engineering mechanics paper course C203. It's a 3 credit course and 4 credit course, and Marx structure you already know. References which will follow are this: vector mechanics for engineers by that is statics and dynamics by Beer and Johnston. This will treat as textbook. There is another book here by Engineering Mechanics by Irving James, and Engineering Mechanics by R.C. Hibbeler. And NPTEL notes you can find online. So those will be a very good help for you. Okay, so let's start this mechanics topic here. In the unit 1, we have to study the fundamental concepts, that is system of units, scalar and vector quantities, characteristics of force, fundamental laws of mechanics, system of forces, 2-force system, 3-force system, equilibrium of a body, equilibrium equations for plane force and space force systems. So this is what we have to study in unit 1. Let's start with the fundamentals of the mechanics. So in this course, actually, we are going to study the basics. Those will be very small topics, but those will be very helpful in your studies of structure analysis, design, etc. So this is a very important paper, very important course which we study at this level. Most of the portions here you have studied in mechanics in school level, 12th level, probably 11th level. Plus, you have studied a lot of mathematics also. So it's a kind of review, but it will be a very good review for you for even you can recapitulate your informations, your references, and you will find it. If you when you will study it from Weir and Johnston, you will find it completely new kind of thing. So here you have studied in units and dimensions. So dimensions here, there are 2 types of dimensions which are independent dimensions, and we call them as primary or derived. So primary or basic dimensions here are space, time, and mass. and derived dimensions are many. One of them is force. So here we have to study basically force. So space, time, and mass, and then force. Let me comment something on these dimensions. So first, let's discuss space. Space is associated with the position of a point P, which is defined by three length coordinates known as coordinates of that point P. It requires a frame of reference. So frame of reference is very important in these mechanics analysis studies. So one frame of reference which we'll stick to is the Newtonian frame of mechanics. So it requires a frame of reference. An inertial frame of reference possesses a property that this frame of reference, in this frame of reference, a body with zero net force acting upon it does not accelerate. If no force is acting in the body, it will not accelerate. That is, such a body is at rest or moving at a constant velocity. So it doesn't have acceleration, but it may be moving also. So this is also known as an inertial frame or Galilean reference frame or inertial space. So you can review, find lot of information. If you do Google this information, you will get lot of definition terms for Galilean reference or inertial frame, inertial space. Time. Another basic dimension is time. Space is not enough to define an event. The time of occurrence of an event is equally important. So time of occurrence of an event, in addition to the location of the body in the space, we need to know. That is an independent of space. Mass. Third basic dimension is mass. The concept of mass describes the size, compares the two boundaries. So basically, the physical quantities which we study, we use the materials, create some structures, geometries, and then using these kind of applications, we create the structures, buildings, dams, bridges, etc., etc. So here they all have mass or they have size, and from this size we compare the two bodies from physics angle. Force represents an action of one body on another. So when two bodies interact with each other, some force we see. So it's an action or reaction we see. So action means something, a cause. Reaction is the effect. So a cause is called an action. Action is force. A force is characterized by its magnitude, its direction, and its point of application. The force is defined by these three specifications, these three entities, and if any of the three changes, the entire force definition changes. So this is how we describe the force. In Newtonian mechanics, space, time, and mass are independent and absolute concepts. In relative mechanics, the time of an event is position dependent and the mass of the body varies with its velocity. In Newtonian mechanics, the inertial frame of reference. So actually, we are not dealing with the bodies, the objects, in which motion is of that extent that the body mass changes with velocity. So in our case, body has some rest shape, rest mass, that is fixed mass. In Newtonian mechanics, the inertial frame of reference is the one in which Newton's first law of motion is valid. This is one important thing. So first law of motion defines the inertial frame of reference. The principle of spatial relativity generalizes the motion of the inertial frame to include all physical laws and the Newton's first law. So the theory of relativity actually generalizes special relativity, generalizes the physical laws, and it includes the Newtonian mechanics also. Absolute space and time. Newton posited an absolute space considered well approximated by a frame of reference stationary relative to the fixed stars. So fixed stars, on the basis of fixed stars, a reference stationary frame was defined in Newtonian mechanics. The inertial frame of reference was then one in uniform translation relative to the absolute space. So if we define fixed stars position, absolute space, then the inertial frame of reference was in uniform motion. Uniform motion means motion with constant velocity. Lange's proposed a definition, a reference frame in which a mass point thrown from a space point in three different directions, non-coplanar directions, follow rectilinear path. Each time it is thrown is called an inertial frame. So when a point mass is thrown, it follows a rectilinear path each time. This kind of frame of reference was defined by Lange.
हेलो सर।
Yes.
सर सॉरी टू डिस्टर्ब यू बट सर बहुत बच्चे ना ज्वाइन करने के लिए बाहर बैठे हुए हैं, उनका ज्वाइन नहीं हो रहा है।
Okay.
आप उनको परमिशन दे दीजिए।
एक ही स्टूडेंट था,
सर 2-3 स्टूडेंट्स हैं।
तो ask them to join. Okay, okay. Non-inertial frame reference frame is the bodies in non-inertial reference frames are subjected to fictitious force are the result of the acceleration of the reference frame itself. Now, reference frame is in accelerated motion, then it applies some fictitious force on the body and not from any physical force acting on the body. So no physical force is acting here. So actually, the examples of non-inertial frame of reference were defined by D'Alembert's principle, that is the inertia forces and centrifugal forces, Coriolis forces in a rotating frame of reference. So these are the examples of non-inertial frame of reference. Physical quantities and units. So as we all know that physical quantities have the qualitative and quantitative description, and they represent measurable properties of physical items such as length, time, mass, density, force, energy, temperature, etc. Every specific value of a quantity can be written as the product of a number and a unit. A numerical value is attached to it, like 10 kg. So kg is the unit, number is 10. So 10 kg is the mass unit, means that mass quantity. So this is how we describe the physical quantities. And say volume 1 meter cube, velocity 1 meter per second, speed say 1 meter per second. So these are the physical quantities you have studied already. Then here we define say a physical quantity. So invariance relation is like this. If G is a physical quantity, G in curly bracket is numerical value and G in a square bracket is the unit. So basic units here are, we follow the SI units in which mass is kg, length is meter, and time is in seconds. So this is how we define the units and we use these units. Here, these units are like meter, kilogram, second for length, mass, time, temperature, Kelvin, current, ampere, intensity, luminous intensity, candela, amount of substance, mole. So this is how we define these basic units. Here there are some more units you have studied. You know a lot about all these. These are some derived units. Actually, they are dependent on some basic units. Then we use here the prefixes to the units like femto, pico, nano, micro, milli, kilo, mega, giga, tera, and nowadays petaflops. Peta is also used. 10 raised to 15 is peta. Petaflops defines the computational speed of supercomputers. So nowadays, petaflop has also become popular. Peta. So these prefixes are used to are attached to these units. Now let's study the idealization of these materials or the particles or bodies. So we usually study the condition of rest or motion of a particle. Here we will study the motion also in this unit. So rest, condition of rest or motion of a particle. Now a particle definition wise we can say when Earth revolves around the sun, then the revolution path is very large, of very large length, and so the Earth can be treated as a very small particle, a point mass. So these particle we can also call them as point masses. So then point mass doesn't mean that a small, very fractional quantity of mass. It may be used mass also, but it depends what kind of studies we are doing, and so accordingly we can change our definition from point mass to rigid body. Rigid bodies are a combination of a large number of particles. We describe it as a continuous material with a definite rest shape. So in our case here, shape of
Excuse me, sir.
will not change. That
Excuse
is,
me, sir.
yes.
सर वो सीआर और बाकी सब बाहर वेट कर रहे हैं लॉबी में, सर उन्हें आप अलाउ कर दो सर.
Okay. Whosoever has joined actually has joined through this link. Do you need link also? This.
No, sir, we don't need link. Only you have to allow them.
Okay, so I'm just admitting. Yes, I will.
Yes.
Okay, fine.
Thank you, sir.
Okay. So we define two types of bodies here: the point mass, and another is the rigid body. Third definition is of elastic bodies. Rigid bodies are those in which we apply forces or there is some cause, they don't deform. So their rest shape doesn't change. And if the center of mass is known, then if we study the center of mass and its motion, then it represents the motion of the entire body. So that kind of body we define as the rigid body. But actually, in the actual structures, they are elastic bodies. So elastic bodies will not necessarily, it's not the part of this syllabus at the moment, in which deformations occur, and because of that particle at different locations, they change their position after deformation when the forces or actions are applied in the structure. So their relative positions also we determine using different methodologies, but at the moment we consider that shape remains unchanged, and body particles, they remain fixed in position, they don't move, they don't deform. So here we have discussed the idealization here of the physical entity, and this we call as say mechanical idealization. We do some mathematical idealization also to analyze, to make analysis simple, but mathematical analysis, assumptions, etc. We introduce assumptions like linearly elastic structure, or we want to perform linear analysis, etc. So those are mathematical simplifications. We are not talking of mathematical simplifications here. We are talking of physical simplifications. A body we define here. Later, we'll use the terms like slender, prismatic, elastic, isotropic, material, etc. So these definitions we attach, assumptions we attach, these are called idealization of the body. So here is point mass idealization or rigid body idealization. This is what we do. So let's study a bit more the rigid body, a combination of large number of particles in which all particles remain at a fixed distance practically from one another before and after the application of load. We define as the rigid body. Material properties of a rigid body are not required to be considered when we analyze it for forces acting on the body. So this is one important thing, that material properties do not change. In soil mechanics, later you will study Here density changes. Suppose we apply the force isotrope. They do not. They are not the isotropic materials. Anisotropic comes in picture. So these things actually material property change. Those kind of materials at the moment we are not discussing. Mechanics of solid deals with all these things, all these variations. So there you will study such variations. One paper, very good syllabus is there, mechanics of solid. So here at the moment, we don't consider, we don't focus on the material property. If any density is there, we consider it as fixed, and so it is not considered in the when we analyze it for forces. In most cases, actual deformations occurring in structures, machines, mechanisms are relatively small, and this is body assumption is suitable for the analysis. In actual structural studies, later you will find somewhere in structure analysis also, even if we treat it as elastic body, but deformations, their relative deformations are small. So some lateral deformations we consider more in, are seen more in comparison to axial deformation. So at times we consider that members are axially rigid. So that kind of constraint we introduce in the analysis. So here at the moment we consider that there are no deformations, so body behavior is completely rigid. Let's discuss another important concept here is the force. Now, force may be distributed force, concentrated force. So here let's focus on the concentrated force. So another idealization of this weight. Suppose this truck is heavily loaded, like 20-ton truck is there. So it's a 200 kilonewton load is there in this truck. Now this 200 kilonewton load is distributed, but we can treat it as concentrated force or concentrated weight, assuming that entire load is passing through the centroid of the body. So when it passes through the centroid of the body, for the purpose of the finding the reactions, I think this kind of assumption is good enough. So this idealization is better. So instead of treating it as a distributed mass, integrating it from in the entire volume, getting the different areas, different loading variations, etc., that would be easy. You want to find out the reaction, what will be the forces transmitted to the tires and then to the ground. If we idealize it as the concentrated force, that would be good enough. So here, depending upon for what purpose we are making the analysis, we introduce certain assumptions. This is called idealization of the forces of the body, etc. So here, basically, a concentrated force requires a definition that if the area through which the load is applied is small, then that kind of force we can treat reasonably, practically, okay, as the concentrated force. So here, say total load is 200 kilonewton, and 200 kilonewton out of 200, the 160 kilonewton, 16-ton load is getting transmitted through the rear axle, and 40 kilonewton or 4-ton loads through the front axle. So this is how this truck is transmitting 200 kilonewton load through tires to ground. And the contact area between the tire and the ground or road is small, so this is good enough to assume that these are the concentrated forces. Now, another thing is laws of mechanics. Laws of mechanics you have already studied very thoroughly in detail, but let's review it here. So, first law, there are three Newton's law of motion we study here, which are the building blocks of mechanics, plus one more law, that is Newton's gravitational law. So, these four laws we study and use extensively in mechanics here in our studies. So, Newton's first law is basically known as the law of inertia. So every object in a state of uniform motion tends to remain in the state of motion unless an external force is applied to it. So if there is no external force present in the body, and in whichever state the body is, it remains in that state. That is known as law of inertia. So here, first law, here we can say, suppose we have considered, we have idealized a body as a point mass, and there are three forces acting on the body, F1, F2, and F3. Body is in equilibrium. Now, when it is in equilibrium, it might be at rest or it might be in motion, and that motion may be uniform motion with constant velocity. If they are not in equilibrium, then they will get subjected to accelerated motion. This is one very important thing. So if they are in uniform motion, they are in equilibrium. Second law is known as the law of causality also. Causality word is used in electrical signals, digital signals, basically to define the things which are happening, or signals which are generating in the positive time in the given reference frame. Usually the sine function, cosine function, you might have studied Fourier theories, Fourier relations, etc. They go to the negative time from 0 to minus infinity, or from minus infinity to plus infinity. Here we treat the things like from 0 to plus infinity. So this is known as the law of causality. And here the change of motion, as we know, Newton's second law of motion, change of motion is proportional to the natural force impressed and is made in the direction of the straight line in which the force is applied, force is impressed. So time rate of change of momentum is force. That is the basic definition of Newton's second law of motion. From that, here the change of motion changes, and motion change of motion, that is time rate of change of motion, is momentum, that is motion proportional to the force applied. So this relation, using this we can derive force is equal to mass into acceleration. And here one thing is there, the force and F and A variable have been used to define the force and acceleration. They have been written as bold faces, while for generating the textbooks, etc., bold faces are good, but for writing manually, bold faces are not good. So we can accent it by an arrow. So on the top of the a letter side force, we can just draw an arrow here towards right or towards left to represent the direction of that vector. So these are the vector quantities and their representation. So here Newton's this, suppose this is the mass, and the moment we apply this force, there is no equilibrating force here, so it will start having acceleration. But again, it comes in equilibrium, dynamic equilibrium, based according to the the D'Alembert's principle on Newton's second law of motion. So when a body is in accelerated motion, then also it is in equilibrium. This is what D'Alembert principle says, but that we'll study later, not right now. So from this we get the acceleration is proportional to force. Here the proportional acceleration induces, and so this relation is force is equal to mass into acceleration. Third law. Third law is also very important law in which action is equal to reaction. Basically, it is this law which helps us in defining the structure of the force transmission. Suppose here there is we translated the force considered as a concentrated force of 200 kilonewton, and then we transmitted it to the two tires. So how this translation happens, how this transmission of force happens in this distributed body force to this tire, that we can work out, that we'll discuss later using this third law of motion. So basically, the first two laws of the Newton are valid only in inertial frame of reference, and inertial frame of reference has a constant velocity. That is, it is moving at a constant, moving along a constant straight line. And third law here is the it means whatever action is there, if two bodies are interacting, one important requirement for the third law is the interaction between the two bodies or two point masses. So what happens when a force is applied on body A and body B is also there, which is interacting with body A, so it will apply an equal and opposite force of same magnitude on body A, and that will be collinear. So collinearity is maintained. So here we can say that forces in the body exist in pair, either inward arrows or outward arrows. Inward arrows here we represent, how do we represent tensile force and compression force, that we'll discuss later. So here this is representing the interaction between the two bodies. So Newton's third law of motion defines this reaction of another mass point adjacent to the first mass point where some force A F is acting, right? So this is a very important relation. Using this, we'll try to generate the path how the load is transmitted from one point to another. Later we'll discuss that. Another law is the Newton's law of gravitational attraction. So law of gravitation here, as we know, two celestial bodies basically to develop for celestial bodies, but it is a very good concept to define the weight of the body also, because weight is another important factor, quantity in our analysis. So that is defined on the basis of Newton's law of gravitation. So as we know, F1 and the two forces, two celestial bodies, they actually interact with each other. They attract, they and some attractive force gets applied between these two masses. So say m1 m2 and distance between them is r. So F is g m1 m2 over r square, and from this g is the gravitational universal constant of gravitation. Based on this, we can define. Now how do we use it in our mechanics studies? Because Earth, we are creating structures, objects on Earth, close to Earth. So here one mass is mass of the Earth, another mass is the mass of the body. So here gme over r square, this entire term defines the acceleration due to gravity. So we define the weight or the gravitational force weight as mass into gme over r square, or mass into g. So this is a very important requirement to define the body weight. So gravitational force, we'll study a bit more on this gravitational forces, distributed forces little later, in some other units probably. So these four laws are the building blocks of our study of mechanics. Here we follow when we define the force, there are maybe two forces, because as we discussed, force is a vector quantity because it requires the direction also, direction and point of application. So if there are too many vectors, then we have some rules, some laws. One law, suppose there are two vectors, we call it as parallelogram law. Parallelogram law was developed by Stevinus quite long back, 500, 600 years back. And it demonstrated that if there are two vectors A and B, we can find the resultant of these two vectors using the law of parallelogram. And that I can explain here. Suppose there are two vectors A and another vector is B, then what we can do, we just shift the vector B to a new location at the head of A. So what do? We connect the vector B with the head of A, tail of vector B with the head of vector A, or vector P and Q in this manner. And if we connect the tail of first vector to the head of another vector, then this vector, if we get a new vector that represents the resultant vector, its magnitude and its direction also. So alpha angle represents the direction. And if you use the Pythagoras theorem and suppose the deflection angle of Q with respect to P is theta, then here we can use this triangle ODC and we can work out the resultant from the Pythagoras theorem. So it would be P square plus Q square plus twice PQ cos theta. When this exterior angle, that is deflection angle, is known, we can establish a relation between P and Q and R that way. So R square is equal to P square plus Q square plus twice PQ cos theta. If it is given, the interior angle is given, this one angle A, then relation changes because this angle A cos theta, now it will be pi minus theta, this angle will be. So in the cos theta, if you substitute pi minus theta, it will become P square plus Q square plus twice minus twice PQ cos theta. So if theta, that way, this relation, if interior angle is given, it becomes negative. So you can derive that on your own. Another law is called triangle law. Triangle law here, this triangle OACO, this triangle we can separate. We no need to draw the parallelogram, but we can separate it. And this triangle also can be used in many locations. We draw a force triangle. We call it triangle, not polygon. When there are three vectors, we call it triangle. There are more than three vectors, we call it polygon. So using that triangle, we can work out the resultant or equilibrating forces, etc., etc. So this law is similar to the parallelogram law, but we use it separately, so we call it triangle law. Now, before we go further in the vector mechanics, let's study the scalar and vector quantities. The scalar quantity here uh, has some numerical value, and we attach it with some unit like length or say liter volume, representing volume 65 liter of petrol, or 60 minutes time required to move from one place to another. So this number is called a number and unit they define this scalar quantity, which is not which does not require any direction to define this quantity. So this quantity we call as scalar quantity. All algebraic operations, multiplications, subtractions, and divisions in same units we can do. We can subtract 10 minutes from 15 minutes, etc. And we can divide, say, like here, 100 kilometer divided by 1 hour. So it gives us, some speed of the motion here. So this way, we can combine these scalar quantities, relate these scalar quantities by multiplying and dividing, right? So vector quantity. In this case, a vector quantity is, as we discussed earlier, requires magnitude, requires direction, and the point of application also. So in this case, actually a vector quantity requires two terms. When we define force, it requires three definitions or three specifications. So this, say, dog, tail is representing the tail of the vector, and head is representing the head of the vector. So a vector and the length of the dog is representing the magnitude of this vector. So it has a tail, it has a head, and a particular direction in which it is getting applied. So, and the length of the, geometrically, we represent this as the magnitude. So suppose vector, this length is, say, 50 centimeter or 100 centimeter, 1 meter something, then it is 1000 mm or 100 centimeter. 100 is the magnitude unit. We can represent it like this. So this quantity we call as the vector quantity. So here there are three important things. One is the tail, another is the head. So at head we have an arrow which represents the direction of the vector, and the length of this vector, geometrically representing the magnitude. Now there is one example here. Suppose somebody is there in the tent and goes to in the morning to the pond, a fishing hole. So how he travels, it may follow different paths, but the displacement or the distance between A and B, a vector distance between A and B, is this quantity. So this is a vector distance traveled from A to B. Is this path may be anything, right? So this is what we mean by the vector. Now here, suppose it's a one-dimensional vector, so there are different operations, algebraic operations we can perform. But in the definition of vector, one interesting thing you see, we define a boldface term. D is for distance, but no need to write boldface. We can write simply D, and we can accent on it an arrow. And so arrow is accented on this letter, and then there is a subscript AC. A is representing the tail, and C is representing the head. So this is how we define a vector. So immediately it tells us that vector is directed from A to C. So A first subscript is the near end subscript is tail, far end subscript is the head. So DAC is directed in this direction. So somebody is moving. So DAC is a positive vector here moving from A to C. And then when it goes, suppose goes back to D in the negative direction. So it is a negative direction, but see negative direction here, arrow is towards right. And now it is going from C to D. So in the reverse direction, but C now has become a first subscript, and then D is second subscript. So it is moving from C to D. And then we can do all those additions, etc. in the DAD plus DCB will be DDB will be equal to DAB. So this is one-dimensional vector. Some definitions of these vectors, like A is parallel to B. Now, to define a vector as parallel, may be parallel or it may be collinear. Their magnitudes are not same, but they are directed in the same direction. So they may place parallel or may be placed collinear. Such vectors are defined as parallel vectors. A vector B, A is placed opposite to vector B, it is called anti-parallel vector. So it has 180-degree direction difference. So it is anti-parallel vector. And A is anti-parallel to A. So they are two vectors of same magnitude but oppositely directed vectors. And A is equal to B when it is equality is there. So A is equal to B, then they have same magnitude, same direction, and they are also parallel vectors. And orthogonal vectors means they are at right angles. So two vectors are at right angle. It may be in any direction. That vector set may be in any direction with respect to reference axis. So, but they are orthogonal. So this is how we define the types of vectors. So we define here particle, scalar quantities, vector quantity, free vector. Free vector is a term used when it is not associated with a unique line space. Point of application here may be there, but it's not in a particular unique line. So only the direction and magnitude of the vector remains fixed, but point of application, I think, is not required to define the free vector. So this is how we define the free vectors. Or free vectors, at times they are used to represent from some entire body. Suppose a vector diagram is there in trusses, etc. So we pick one element, that free length independent of other points we call as free vector. Sliding vector is a very important concept here. Sliding vector, when we move the, we slide the vector in the same direction, same line of action. Now see here, based on this, there is a law of transmissibility, principle of transmissibility is there. One vector has line of action as shown here on this body. Initially, it is applied at this point, and then we have shifted the point of application on the same line of action to another point. With this kind of shifting, it doesn't modify any effect on the body. So body will have similar effects what we see on the left side and what we see on the right side. Such kind of vectors are called the sliding vectors. And in this case, actually, we'll discuss later, if possible, if required. Yeah, I think somewhere we have to study this. So law of transmissibility will derive these values also. So we find that suppose one vector v by 2, you reduce it to half here, reduce it to half here. So v by 2 here, v by 2 here, they will produce the same effect on the body as a single vector. So this is the sliding vector. And another vector here is bound vector. A bound vector when it has some fixed point of application, like A here. So this is a fixed vector or a bound vector, which is bounded with a point of application. So that is the definition of free vector, fixed vector, and sliding vector. Now some mathematical operations which we do with these vectors. So suppose two vectors are there, A and B. We find the resultant by using the parallelogram law. So vector addition R is equal to A plus B. This is how we write it mathematically, but R is not algebraically equal to A plus B. Suppose this is 3 meter, 4 meter, it is 5 meter, R is 5, but is not 3 plus 4 is not 5. So their numerical additions, algebraic additions are not equal. This is the vector addition. Here there is another vector that is a negative vector. B is positive vector in this case. So if it is a negative vector, then here you see A minus B. So what we can see, actually when we write, there are two methods here actually to write these vectors. One is just drawing parallelograms using parallelogram approach, or another is called connecting the vectors from tail to head. Head to tail connection. So that is called head and tail method. So we'll use that extensively. It is better than arranging it in parallelogram. So here you see B is directed like this. So and then the D vector here is not this vector by connecting this diagonal from this end to this end, which we obtain here. Rather, it is an opposite diagonal. And then we can say from our concepts of tail to head connection that B and D are an orderly connection in the same order. If we are moving in clockwise direction, then B is towards right, then D is in that clockwise pattern, but A is opposite. So from this relation, we can say that B plus D is equal to A. So A is representing the resultant of B and D. So B plus D is A, or if we bring B to the left hand side, so A minus B is D. So if this D, this diagonal, opposite diagonal of this parallelogram is representing A minus B. Again, A minus B is not equal to D algebraically. These kind of vector approaches we use in such a huge areas like mapping a country, creating the geodetic maps, etc. So that we will study in surveying in later courses. So this is where we use these vectors. And then suppose there are n number of vectors, their positions are given in this body, their point of applications are known, magnitudes are known, so we can connect them together to find the resultant effect on a body in this manner. So we connect these vectors like from tail to head, and the tail of new vector is connected with the head of the previous vector, and this way we reach to all the vectors, and then connecting from tail to the head of the last, tail of the first to the head of the last gives you the resultant vector. So this is how we connect these vectors. Now one more example here, one very interesting example. There are two vectors here. One A vector is 10 units directed like this, and vector B is 7 units directed like this, and the angle between these two is 145 degree. So if you want to represent A plus B, it would be in parallelogram will be represented by this diagonal, right? And if you want to represent A minus B, it would be represented in this manner. Now, using tail to head method, we can do a very interesting change in this approach, parallelogram approach, and this method is far superior than this approach when we do the vector calculations. And usually, when large number of vectors, more than 2 are there, then parallelogram is not suitable. So we go for this method, tail to head method. So in this, what we do, this B vector is directed downward here, and A is directed, say, in this direction upward. So what we can do, because B vector is a negative vector we have identified here, so we can replace this B by minus B vector and change its direction. So now here we have changed tail to head and head to tail. So here was head, so we made it tail, and the head of B, tail of B we have made to head. So now this way, this is minus B plus A, and then if we connect the tail of B to head of A, this will represent the resultant vector and its magnitude and direction. So this is another approach for the vector addition, in which this larger diagonal represents A minus B, whereas here the larger diagonal represents A plus B, something. So this is a very good approach in vector mechanics. So let's summarize our study. We have studied a vector quantity vector quantity is any quantity that has magnitude and direction, such as displacement, velocity. Vector quantities are represented by mathematical objects called vectors. Geometrically, vectors are represented by arrows with the end marked by an arrowhead. The length of a vector is its magnitude, which is a positive scalar. On a plane, the direction of a vector is given by the angle the vector makes with the reference direction. Often an angle with the horizontal, and this angle is usually with the horizontal. The direction angle of a vector is a scalar quantity. Two vectors are equal if and only if they have the same magnitude and direction. Parallel vectors have the same direction angles but may have different magnitudes. Anti-parallel vectors have direction angles that differ by 180 degree. Orthogonal vectors have direction angles differ by 90 degree. And here one more point before we end is when a vector is multiplied by a scalar. So when we multiply by a positive scalar, it modifies the original vector. So its magnitude changes, but direction remains same. But if we multiply it by a negative scalar quantity, its magnitude changes, but direction also, its magnitude and direction both get affected. So magnitude and direction both change. So multiplication by a negative scalar reverses the original direction. The resulting vector is antiparallel to original vector. The multiplication by a scalar is distributive. This distribution law we'll discuss later. Vector can be divided by a non-zero scalar. So we can either divide or multiply in a vector a scalar quantity, but we cannot divide a vector by a vector. Two or more vectors can be added to form another vector, and this vector is known as the resultant vector, and this operation can be done using the parallelograms. So we can add the vector to vectors, scalar to scalar to scalar, but we cannot add a scalar to vector. This vector addition is commutative and associative. This will prove the right later. To construct the resultant vector of two vectors in a plane geometrically, we use the parallelogram rule, and to construct a resultant vector of many vectors in the plane geometrically, we use the tail to head method. So this is what we have studied today. Let's stop here. Please write something on the chat board. For attendance, I'll record it. I'll take the copy of that, and I'll save it as attendance. Thank you. Thank you very much.
Excuse me, sir.
Dhruv is present.
Yes, sir.
Dhruv,
Sir.
please, do you have any pros to record the attendance of the students?
Yes, sir. I have Excel sheet so they can mark their attendance there.
Yeah, please request all to, so that you can generate parallel attendance, which we can verify together later.
Dhruv, can you share the link in the chat box?
Wait a minute, I am sharing.
Yeah, please send for the attendance. And I request all of you to please write something, say hello to me, and then here in the chat board, your attendance will come. I'll copy it and record it in the Excel sheet, and later I'll rearrange it to convert into your attendance. Thank you. Thank you very much.
Thank you, sir.
Sir, I shared the link in the chat box so they can mark from there.
Okay. But this I am also keeping as a record. So we'll match. If any discrepancies there, I'll modify.
Okay, sir.
Dhruv, do you know any student, Anil Khav?
No, sir. Anil
He was
Khar.
one of my students of MTech out here, quite long back, 6-7 years back.
Okay, sir.
So all of you have entered your remarks in the chat board. Thank you. So I'm just copying it now.